volunteer to host this. I'm one of Vera's students. My name is Matt. I also work with Dickie Lead. Today we're going to hear from Daniel. Daniel did his undergrad in computer science here, where he did some great work with Nathan Weed, which is how I met him. So it's my pleasure to introduce him today. And now he's currently working on other cloning algorithms as a researcher at Xanadu. So.
Thank you, Matt. So today I'll be talking about our recent work on nonlinear spectroscopy via generalized quantum phase estimation. Before I get into all the algorithm and the math, I just want to spend some time motivating the problem because it can get a little complicated. So first, what is spectroscopy? Well, basically, spectroscopy is the study of how molecules and matter interacts with light, or more generally, a electromagnetic field. And it turns out that if you look at how the molecule interacts with these fields, you can actually learn a lot about the molecule, which helps you design materials for a variety of different technologies. For instance, X-ray spectroscopy, in particular, X-ray absorption spectroscopy, is the main approach in studying the redox process occurring in cathode material for batteries. So by being able to simulate these processes, you can gain insight into how new materials for batteries would work, and you can hopefully make better batteries. Yeah.
I just want to point out spectroscopy, like it's not limited to light, but mass spectroscopy, like spectroscopy that's not like the spectrum, it's about having a spectrum, and rather than just like this is light spectroscopy. Just pointing that out.
I mean, like other than electromagnetic fields?
Yeah, mass spectroscopy.
Well, spectroscopy is actually part of a bigger framework called response theory, which is originally what we developed this for, but as a subsection of response theory, we have kind of light matter interaction and how optical properties of materials, for instance. So batteries, that's one application. My colleagues at Xanadu actually had a paper fairly recently on how you would simulate X-ray absorption spectroscopy of battery materials on a quantum computer. So if you wanted more information on that, you can check out that paper. Other than batteries, we have molecular or chemical fingerprinting. Basically, vibrational spectroscopy and Raman spectroscopy let you fingerprint material in the sense that different molecules have particular vibrational spectra. And vibrational spectra is actually something you can measure fairly easily. For instance, if you've been to an airport where they kind of dust your laptop or whatever you have, your luggage, what they're actually doing, they're then going to put that dust or whatever they collected into a spectrometer and look at the vibrational spectra, the near infrared kind of spectrum. And they match that fingerprint to a database that they have for different kind of molecules, for which they're able to detect if you have anything dangerous or something explosive, for instance. Interestingly enough, this is also used in forensic. So you can do fingerprinting of actual finger marks on a crime scene to figure out the different kind of chemicals that were present in the crime scene. Another example of this is in pharmaceutical. There's actually kind of handheld devices, spectrometers that let you kind of point at something and get its vibrational spectrum. And then if you have a database to compare to, you can figure out what the composition of the material is. Absorption spectroscopy is an important one, which has a lot of applications itself. For instance, in photovoltaics, if you want to design solar cells, you better know kind of what wavelengths of light you'll be absorbing. Speaking of solar cells, we just recently, last night, published a paper on Archive describing a new algorithm for performing vibronic dynamics. And we showed how you can use this algorithm. It's actually very optimized, and the numbers we're getting are really good. How you can use this algorithm to design better solar cells based on a quantum phenomena called singlet fission. Now, if you combine that algorithm with the spectroscopy stuff that I'm going to present here, you can do vibronic spectroscopy, which is itself important. But in that paper, we don't look at spectroscopy, but we look at the different observable, which is actually a lot easier to measure, which is state populations. Anyways, it's a bit of a plug. Moving on, there's absorption spectroscopy, there's emission spectroscopy. Emission spectroscopy has a lot of applications as well, for instance, in designing better lasers or LED technologies, in particular OLEDs. By looking at kind of the absorption or emission spectra of an OLED organic LED, you're able to study properties such as what color of light or what wavelength of light you will be emitting, which corresponds to the color. Kind of the intensity gives you the brightness. The width of the peak would correspond to the color purity of the material. Yes.
Agree that spectroscopy is useful, but just why is it useful when you have like generalized quantum phasor which are applied to it, and why you want to keep manual? So like those are like we agree spectroscopy is useful. Nobody's going to doubt that.
Well, for one, you're not actually performing the spectroscopy. You're simulating. Being able to simulate spectroscopy experiments on a quantum computer is a lot different than actually having to synthesize material, go to a lab and do the experiment. Second, the framework I'm going to present here also includes linear spectroscopy, but the whole idea is that you generalize it such that you have nonlinear spectroscopy, and things like Raman spectroscopy are nonlinear responses. So,
like, why is that useful? Why is it useful to generalize it, and why is it useful to make it nonlinear? So things that don't mean that when I wanted to like just to see how it's motivated.
I think what I've been doing for the past 10 minutes has been the motivation as to why you would want to do that. I don't see I'm not sure what you're asking.
It's just spectroscopy.
Right?
Yeah.
So spectroscopy is important. It lets you study materials. If you can simulate it on a quantum computer, you don't have to go to a lab and do all of this. So you save a lot on doing that.
Like that's the easy part. The hard point is why you want to take this approach to do the spectroscopy, to simulate the spectroscopy.
Could I suggest we let the speaker carry on and maybe this will become clear?
Sure, yeah, of course.
Yeah, so you still haven't seen the actual approach. So this is kind of motivation as to why you would even care about what I'm about to present. So moving on, before we generalize quantum phase estimation, just let's think about what is quantum phase estimation. Maybe someone from here want to answer that. What is quantum phase estimation? What is it trying to do? Are you guys, just by raise, how many people have heard of quantum phase estimation? Most of it. I guess, okay. What is quantum phase estimation trying to do? What typically people talk about is that you have some state, an eigenstate, for instance, and you want to get the energy of that eigenstate. I'm sure, as you all knew, but refused to answer. But and if you have a linear combination of eigenstates, then you have you end up sampling from the spectrum of that state, in a sense, where you have an overlap with different eigenstates, and that is the probability of the energies that you're going to sample. So one way to think about it is what is really trying to do. The goal, if you can have like the perfect outcome out of phase estimation, is to estimate this function, which is the Fourier transform of the expectation of your state with respect to a unitary represented as e to the iht. To make it more concrete, for instance, say your state is a linear combination of eigenstates. You can decompose it as a linear combination of the eigenstates of the Hamiltonian or the unitary. Then the Fourier transform here actually becomes kind of a function where at frequency omega, you're going to measure the overlap of the states with all the eigenstates that have frequency omega. Now, again, this is not what you would get out of the algorithm. This is kind of like an infinite precision with Dirac delta, but I'm trying to motivate the problem it is trying to solve. So if you look at what QP is trying to do from this angle, this is how we're going to then generalize it to do more cool stuff with it. So generalization, quantum phase estimation, the way we generalize QPE along two different kind of axes, I guess. The first thing is to, let's say, from slide before, I said, oh, you have the expectation, you want the Fourier transform of the expectation with respect to some time evolution operator. Now, let's say we extend that and say we want to do phase estimation on interaction picture operators that have, for instance, this form. The observable A at T times B, for instance. Now, if you put that operator in between the state that you're starting with, now here for simplicity, let's assume it's a eigenstate. Otherwise, you would have that kind of the amplitude, the norm of the amplitude squared here with respect to n. But let's just assume you're in a eigenstate, a perfect eigenstate. This is what you would get. This is the quantity. Then another thing you can say is that, okay, now what if we want to do a multivariate phase estimation where you have, instead of an operator, the time-dependent operator that is only dependent on one time variable, what if our operator is dependent on multiple time variables? For instance, what you have there. Now, if you work out the math, you get some complicated expression that looks like this. Now, we'll connect this later to spectroscopy, but this is kind of what you will be estimating, or this is the perfect thing that you would want with infinite precision. By the way, some of you might know already, these are correlation functions. So this, the 1D case, this is a 2-point correlation function between operators A and B. And then you can generalize that to have correlation functions between many different operators. And that's what you would get here. So, okay, this is cool. This is, I mean, you might say, Daniel, you just like generalizing things. So how is this connected to anything useful? Actually, sorry, before that, I've kind of talked about this a little bit before, but what you really get with QPE, you cannot get infinite precision, obviously, but you would get some approximation to the quantity you would want, which then corresponds to, you have to replace this delta function with a window function at broadening. And generally, if you want this window to have width eta, the amount of time you would need to do with traditional QPE is 1 over eta. This is the Heisenberg limit. And you can then, again, extend this idea of windows to the multivariate case where all of those deltas are replaced by a window. You could obviously have different windows, but just for simplicity, let's say it's a single window. In QPE, this would correspond to your accuracy with respect to which you actually get the energies. And you want to make this window as narrow as possible. So basically, having a window is, you don't want that. Technically, you want the direct delta. But here, for spectroscopy, this can actually be a feature, not a bug, because a lot of times you have broadenings in your when you're doing spectroscopy, you want to have some broadening to account for different kind of relaxations that happen. Now, what does this look like? I will expand this later, but at a high level, if you have D time variables and you want to do a multivariate phase estimation, you, instead of having one time register that you have in regular QPE, you would have D different time registers. And then here's the initialization of the window. So basically from the previous slide, QPE, some of you might notice what this is, when you talk about regular QPE, the window function that you're looking at is a sync function. So you basically have like a uniform superposition. That's where the Hadamard's come from, and that leads to a sync window. But if you want to have better probability of success in regular QPE, you can use different window functions by initializing the state that is going into QPE in the time register beforehand. For instance, I think the optimal one is a Kaiser window you can prepare, or you can do a Gaussian window depending on what you want. So here we also have these initialized. So this is kind of the unitary that prepares that superposition of the coefficients in the Fourier series representation of the window. After the QFT, this kind of turns into the actual window. But this is what those are. In regular QFTs, these are just a bunch of Hadamard's. Then you have your state preparation unitary that prepares your state going into QPE or multivariate QPE. And then you have this multiplex operator that you apply to the state register, where depending on the state of the multivariate state of your time, you apply the different operator. Now, the whole point of this is that this is can be done really cheaply. If you had to kind of enumerate all these different things, it would have exponential costs. But just like QPE, where you can only do kind of powers of U, we're going to use the same principle, and it applies here. And let's just do this very efficiently, which I'll show on the next slide. And then at the end, you do the quantum Fourier transform on all your time registers to take them into the frequency domain. And then you do a kind of an unpreparing of your initial state preparation by applying the U dagger that prepared your state originally. Now, this is kind of not very clear what it looks like. Let's talk about the concrete case. Let's talk about a 2D phase estimation, the two-dimensional phase estimation. If you can't see the bottom, this is kind of what I had previously, but up to only 2 variables. And I'm basically expanding it. As you can see, it has a very similar structure as QPE. So with QPE, you're used to seeing just something like this. Now, so this is the forward, for instance, time evolution or time evolution. And in your operator here, it's kind of, you apply it in order. You apply the perturbation, you apply the forward time evolution, the second perturbation, and the backward time evolution. So this part would correspond to kind of the time evolved perturbation. And then you would do it for the other register as well. If you have, in this case, you have 2 registers, so you have to go through and do these in order. It looks very similar to QPE, uses the same structure. Now back to my question of, okay, this is cool, but why do we care? Why do we want to do this? Well, I mean, as you might have guessed from the title of the talk, we want to do spectroscopy. So connecting what I just showed there to spectroscopy, application of spectroscopy, you want to say, calculate or sample from the absorption spectrum of some system. The absorption spectrum of a system corresponds to the correlation function of the dipole operator with itself, commonly referred to as the autocorrelation, which looks like this. So from the first slide where this is still one variable, where we had A and B, we say A and B are the same thing, the dipole operator. And we choose some kind of broadening for our spectrum, let's say Lorentzian, that's one of the common ones often used. Then by just replacing everything here on the previous slide, where we had, so U, then you would have UT, you're able to directly sample from the absorption spectra. And because you're directly sampling from this, you can simultaneously estimate the correlation function at all omegas, because you can, model the intensity of each omega, the height of each, bin that you would have that gives you these peaks as a Bernoulli variable. And every time you sample something, that corresponds to like a success for that particular frequency and a failure for everything else. And then you can simultaneously estimate all the peaks. Yes.
For the Fourier transform.
Well, depends. So like if you talk about the autocorrelation function just in the time domain, then yeah, it would be the Fourier transform. But I mean, in the paper, we kind of refer to them as either response function or autocorrelation or correlation function in time versus the frequency domain. So autocorrelation in the frequency domain, which would be the Fourier transform of the time domain version.
I don't know.
So this was the first kind of change that we made to QPE. We're still working with one variable. Using this, you can do something like absorption spectra, which is a type of linear spectroscopy. Now, if we use the multivariate version, we can do things like nonlinear spectroscopies by doing the multivariate phase estimation. There's a whole zoo of nonlinear spectroscopies out there, and I'm not an expert on every different type of spectroscopy, but generally, for instance, simple third order spectroscopies would look like this. Now, if you do things like, sometimes you can do like omega-1, omega-2, and then this one is omega-1 plus omega-2. So it turns out to be like a two-dimensional, two-variate function that corresponds to a specific type of Raman spectroscopy. And there's a whole lot of different things you can do with it. Yeah. Any questions at this point?
Or you just trying to find the spectrum of operator or of the Hamiltonian? Is that the spectroscopy?
Yes. So you have let's say you want to do absorption spectra or nonlinear spectra of some molecule. You would construct the Hamiltonian for it, then map it to the qubit Hamiltonian, which you can use like a Hamiltonian simulation to do the time evolution. And then you get the absorption spectra of that specific material or molecule.
Limited to, so is it limited to Hamiltonian eigenspectrum, or is it also like those other operators eigenspectrum?
What is an example of another operator?
Like any operator, I don't know, any operator.
Yeah, so anything that you can exponentiate, right? It's as long as it's a Hermitian operator that you can do e to the IHT. So we kind of assume any e to the IHT, and you get the spectrum with respect to that one. And like I said before, I didn't want to get into this. I didn't include a lot of that in this presentation, but there's this bigger framework of response theory where basically you look at how the value of an observable changes over time as a result of a different perturbation. And there, the first order would correspond to kind of this correlation with A and B. So A would be the observable, B would be the perturbation here, and then you would look at how the values of that change. And then the higher order stuff would, there's a whole framework for it, but I didn't want to include because the math is it gets pretty messy, and it's, unless you have already known about it, it's not something you would just look at in a presentation and be like, okay, it makes sense. So I just kind of included the dipole stuff. Yeah, and the cool thing about our method, is that you can directly sample from the spectrum. So it's not that you choose one specific omega and you go and calculate it. You just do everything at the same time. There's another paper that came out almost right before ours. from some people at Berkeley, Guanghao's on it. They use a different approach. They use a quantum signal processing approach where they bin, so that they do these bins. And there they have to search for specific omegas where you can't really sample all omegas. And generally speaking, you don't know where these peaks are. So by sampling is where you figure, oh, this is my peak, for instance. But if you have to search through all different omega values, that wouldn't be very efficient. So that's one of the main, I guess what you were asking earlier, why you would want to do it using this method, is that you can directly sample and estimate everything at the same time. Yeah, so I thought it would be longer. No, he's the only person asking questions. You guys are very quiet. Is this it? Yeah. I guess thank you for listening. Question? Sure.
So like you